So for question number 1, we're going to be drawing water, H2O. So that is the molecular formula for water. So that's part A. So for part B, we need to show the layout and with the electronegativity values. So water, we've drawn a lot of Lewis structures by now. So let's draw water. Okay, so hydrogen, these should be memorized. So hydrogen has 2.2 as its electronegativity, and oxygen has 3.5. Okay, let's determine if it is ionic or covalent. So to determine if a bond is ionic or covalent, you want to compare the electronegativity values, the difference in electronegativity values. So 3.5 minus 2.2 equals 1.3. This is less than 1.5. If the electronegativity difference is less than 1.5, then it is a covalent bond. If it is greater, then it would be an ionic bond. But this is less, so this is a covalent bond. So water has covalent bonds. So for part D, what are the number of valence electrons? So oxygen we know has 6, looking at the periodic table. Each of the hydrogens have 1, so 2 times 1. So that gives us 6 plus 2 is 8 valence electrons. So now we need to determine if it is hyper, hypo, or octet. So water, the oxygen in water, that's just normal octet. So there's no reason why it would be hypo like BF3, like boron, and there would be no reason why it's hypervalent like SF3 with sulfur or phosphorus, for example. So are there multiple bonds or resonance for the structure? No. In water we know it has single bonds, so there's no resonance structure. So let's move on to part G. So the Lewis dot structure of water is, so with oxygen in the center, so let me rewrite the molecular formula, H2O, we have single bonds. So let's give, so each of the hydrogens are happy, they have their 2 electrons to, and then oxygen has to have 8, it's octet, so 1, 2, 3, 4, 5, 6, 7, 8, and the number of valence electrons is correct, so this has a formal charge of 0. So how many electron-rich regions are there for the central atom? So let's see, there's 1, 2, 3, 4 regions. So then what kind of geometry does this indicate? This indicates tetrahedral. 4 regions is tetrahedral. So what kind of hybridization do we have in the central atom? We have sp3. So a good way to remember this is because there are 4 regions of electrons, or 4 electron-rich regions. sp3, pretend that there is a 1 here, and so this is 1 plus 3 equals 4. So the hybridization of a tetrahedral structure is sp3. Now we want to look at what is the bond angle. So this is again something just you need to memorize. For tetrahedral, all the bond angles are around 109.5 degrees. However, due to the electron pair repulsion, the bond angle is going to be a little bit less than 109.5. Now we want to look at the bonding pairs. So how many bonding pairs of electrons are there? There's 2 bonding pairs, 1, 2. How many unbonded pairs? There's 1, 2. So also 2 non-bonding pairs. Okay, so let's do N. So N says, what is the molecular geometry? So we have the central atom and we have 2 bonding pairs and 2 unbonding pairs. So the B stands for bonding and the U stands for unbonding. So let's draw the VSEPR structure. So oxygen is in the center. So this wedge means that the hydrogen sticks out. And then H, this hydrogen with the line just means it's like, think of it flat on the paper. So the hydrogen is sticking out, whereas the H is flat. And then you have the 2 electron pairs. So that is part O. So for part P, to draw the dipoles, so dipoles are always drawn with the arrow towards the more electronegative atom. So in these 2 bonds, the O is more electronegative than the H's, right? The H's are 2.2, whereas the oxygens are 3.5. So what's the difference? What's the electronegativity difference? 3.5 minus 2.2 equals 1.3. The change in electronegativity. So each of these dipoles is 1.3. Again, remember that the dipole, the arrowhead points towards the more electronegative atom. So how many sigma bonds are there, or pi bonds? So pi bonds correspond to, you only find pi bonds in double bonds, right? So sigma bonds are single bonds. So in water we have 2 single bonds with hydrogens and oxygens. So part Q, we have 2 sigma bonds. So is this molecule polar or nonpolar? It is polar because there is a net dipole. See, both of them are pointing this way, and so there is a net dipole going up. So definitely for water, it is polar.